First type of compounds we're going to take a look at are ionic compounds. Binary ionic compound. Think about what the term binary means. Binary means two. So we're going to be dealing with compounds of this type being made up of two elements, one metal and one non-metal. So in looking at the metal is going to be a cation which only has one definitive charge. That name stays the same as the elemental name. The anion, however, the ending is going to change to IDE. So if you notice here, we see IDE at the end of all of these names. So putting together binary ionic compounds, we're going to take a look at some shortcuts for writing formulas. Last chapter we looked at predicting formulas for ionic compounds using Lewis structures and electron dot diagrams. Now we're going to learn a shortcut. So, lithium nitride. Lithium, what column is it in? It's in column 1. So its charge is a positive 1 charge. Nitride, that comes from the element nitrogen. Symbol N, charge 3 negative. So we know that compounds have to be electrically neutral. So I'm going to end up needing 3 of the positives to balance out 1 of the negative 3. So my subscript for the lithium will be a 3. My nitrogen will be a 1. Another way that I can think about that is that taking this digit will become the subscript for the lithium. This digit, which is understood to be a 1, will become the subscript for the nitrogen. But I don't have to write the 1. Just putting the N for nitrogen symbol, it is assumed to be 1 nitrogen. Cesium hydride. Where do I see cesium? Cesium is in column 1, again, positive charge. Hydride comes from hydrogen, and when hydrogen is the second element in the compound, it will carry a negative charge. We'll see hydrogen in some cases having a plus charge, some cases having a negative charge. In this case, it will be the negative, since we're looking at it's acting as the anion, which has to be negative. So what do I notice here? I notice that these two charges will actually balance out. So my formula would be simply CSH. Calcium phosphide. Where's calcium on the periodic table? Second column, so it has a 2 plus charge. Phosphide would come from phosphorus. Looking at its location, it has a 3 negative charge. Again, putting this together, this digit becomes the subscript for the calcium. This one will become the subscript for the phosphorus. So I have Ca3P2. Naming. Again, when I look at these names, I see metal, non-metal, and this is a common compound. Sodium, and the cation name stays the same. And I see chlorine as my second element, but the ending will go to chloride. So I have sodium chloride. Next one, potassium. That doesn't change. Iodine becomes iodide. Again, the ending changing to IDE. And the last one, calcium sulfide. Sulfur sulfide. So, binary ionic. 2 elements, a metal and a non-metal. I look at their position on the periodic table to determine their charge. Then I have to balance out the number of positive and negative ions so that the compound will be electrically neutral. So when we think about elements that only have 1 charge, we're looking at the metals that we find in group 1, 1A, 2A, Group 3A, the most commonly used metal there would be aluminum. Again, those elements, or the representative elements, only have one charge. Now, we will encounter some ions that have multiple charges, and where we find those in the transition metal group. So here's a table, and I think there's a similar table probably in your book that show you several of the elements that have multiple charges. And these are generally some really old elements. Copper. Notice copper 1 and copper 1 ion. Copper 2, the 2+ charge, becomes a copper 2 ion. Roman numerals will indicate the charge of the ion. Now, look at the difference between the stock name and the classical name. So copper 1, cuprous, copper 2, cupric, iron 2, ferrous, iron 3, ferric. There's a definite pattern here between the ending of the classical name and the ion's charge. Okay, if you notice, I'm looking at the OUS endings here. Those correspond with the ion that has the lesser charge. Okay? And the IC ending is going with the ones that have the larger charge. Now, if you notice here with mercury, I didn't circle mercury in the OUS. We might think that the mercury 2 ions are the same, but they aren't, because this one with the asterisk is what they call a diatomic ion. Notice the subscript Hg, and there's a 2 subscript. So what that's meaning is that I have 2 of these put together to make this, which essentially the mercury has a +1 charge. That's why you see that one being called mercury 1 ion, even though you do see the 2+ there. So just a few examples of the ones that have multiple charges. Again, we find those in the transition metals. So how do I deal with those that have more than one charge? Well, I pay attention to the Roman numeral. So manganese 4, which means I have manganese, and since it's Roman numeral 4, I want the 4+ charge. Oxide comes from oxygen. It has a 2- charge. Now when I put these two together, I might, and if I use the crossing method, I would end up with Mn2O4. But what I need to remember about ionic compounds is that I must show a simplest ratio. So I need a simplest ratio here, which will be 1 manganese for every 2 oxygens. So if I think through my thought process up here, okay, I need 2 -2s just to balance out that 1 4+. So ionic compounds always show simplest ratio. So if your subscripts can be reduced, they need to be reduced. Tin 4 chloride. Tin, Sn, 4+, chloride has a negative. Put that together, we have SnCl4. Chromium 3 chloride, chromium with a 3+ charge, chloride again with a negative charge, CrCl3. Okay, naming. CuCl2. Excuse me, CuCl. So when I look at this, I see copper and I see chloride. Now, what I have to think through is what will be the charge of the copper. Copper and chlorine have this 1-to-1 ratio. What do I know about the chlorine? Well, it has a -1 charge. So if I only have 1 copper, it is going to have to be a copper with a positive charge. So this would be the copper 1 chloride. HGO. Now I know that oxygen's charge is 2 negative. And there's a 1-to-1 ratio between mercury and oxygen. So mercury would have to be the 2 plus. So I would have mercury 2 oxide. Again, notice the ending is still changing to IDE. Next, again, you could use this cross method idea to also determine your Roman numeral charges. Because where did this 2 come from? It came from the charge of the oxygen. Does that make sense? Yes, because oxygen's charge is 2 negative. And this 3 came from the charge of the iron. So oxygen's charge is 2 negative, iron 3 plus. Put that together, and we have iron, Roman numeral 3, oxide. In other words, rust. We also have compounds which can contain polyatomic ions. Okay, remember what a polyatomic ion is. Okay, polyatomic ion, covalently bound group of atoms that carry a charge. It is a group of atoms that must be kept as a group and always shown as a group if we would happen to have more than one. Now, looking at the ions, you have a chart on the back of a periodic table. There's some charts in your books. Again, what we notice about most of the polyatomic ions is that most of them end in ATE, ITE. Okay, if we look here, ATEs, ITEs, ATEs, and ITEs. ATEs and ITEs. Okay, we do have an occasional IDE. Alright, so some common ones with the IDE ending: cyanide, hydroxide, peroxide. So there are a few that do have a different ending. Those ones you just have to remember. But most of them can be identified by the ate and the ite ending. We do have a few positive polyatomic ions, ammonium being the most common one. When you start talking about acid-base chemistry, the hydronium ion will come into play. So looking at compounds that have polyatomic ions. Okay, sodium hydrogen carbonate. I know this contains a polyatomic ion because what do I see here at the ending? ATE. Now, hydrogen carbonate. Okay, I know sodium is Na. But what is hydrogen carbonate? Well, could I figure it out? On our back of our periodic table, we probably see carbonate, which is CO3 with a 2 negative charge. But I want hydrogen carbonate, which means I'll have a hydrogen along with that, which would have to have a positive charge. Now, balancing this out, I end up with HCO3 plus 1 and a negative 2 ends up to be a negative charge. So hydrogen carbonate is HCO3 negative. And when I put these two together to make the formula, it's a 1-to-1 ratio. I just put them together and I have sodium hydrogen carbonate. Sometimes you also see this called bicarbonate because remember, bi is a prefix that means hydrogen. And you can apply this concept with more than just hydrogen carbonate. Maybe you have hydrogen sulfate, hydrogen nitrate. You can have some, or not hydrogen nitrate, but hydrogen sulfate, hydrogen phosphate. So you can apply this technique to figure out other polyatomic ions as well if you don't know what they are and can't find them on a chart. All right, zinc nitrate. Okay, zinc is a transition metal. However, zinc only ever has a 2 plus charge. No Roman numeral to tell us that. So we're going to have to just remember zinc 2 plus charge. Nitrate, ATE ending. So if I look on the back of my periodic table or a chart in your textbook, we see that nitrate's formula is NO3 carries a negative. So looking at this ratio, it looks like I'm going to need 2 nitrates to balance out the zinc. In other words, when this 2 has to become the subscript for the nitrate, I will need to put the nitrate in parentheses, and then I will put the 2 outside the parentheses. Again, I need the parentheses to show that nitrate NO3 is a group of atoms, and I need 2 complete groups. Potassium bromate. Potassium, first column on the periodic table, plus bromate, BrO3 negative. Again, 1-to-1 ratio. Okay, BrO3 would be my formula. Okay, then finally, iron 2 hydroxide. Again, I see Roman numeral here. Fe, 2 plus charge. Hydroxide is that oddball polyatomic ion that has the IDE ending, OH negative. So putting these together, I would have Fe. I'm going to need 2 hydroxides. So my OH group has to go in parentheses, and then I'll put the 2 outside. Iron 2 hydroxide. Okay, next 4 we're going to take a look at naming. Okay, with the exception of the ammonium ion, the very first element listed is going to be our cation. The second part is our anion. Now where did this 2 come from? This 2 came from the charge of the sulfate. So my formula, or my name of this compound, is going to be sodium sulfate. Next one, K, is potassium. And the PO4 group of atoms, this was its charge, is called phosphate. So I have potassium phosphate. Next one, Mn is manganese. OH, hydroxide. But what I notice here is manganese is a transition metal. So what will be the Roman numeral that I will need here to complete this formula? Well, what do I know about the OH group? Well, it has the -1 charge. So I have 2 of those based on this formula. And my manganese would have to have then the 2 plus charge to balance it out. So my Roman numeral will be Roman numeral 2. Last one, Na, sodium. CO3, this 2 came from the charge of the CO3, which is carbonate, sodium carbonate.